Okay, so we are continuing on chapter 13. We got into really the major topic of the season here, which is equilibrium. Remember that when we're dealing with equilibrium, we are talking about really a certain type of reaction, which is a reversible reaction. And again, those are reactions, again, that have arrows heading in both directions. Uh, it has a forward direction, which goes from reactants to products. As we talked about at some point, you'll build up enough products that they will actually recombine and head in the opposite direction, which is known as the reverse direction in this sort of reaction. Now, again, as we talked about, one of the important things about equilibrium is this. It again does not mean that you end up with the same amount of everybody on both sides of the arrows. When it refers to reaching chemical equilibrium, we're actually talking about kinetics, and we're actually talking about the rate. And we're talking about the rate of the forward reaction will equal the rate of the reverse reaction. So essentially what that does, as we talked about, is it will pretty much lock everybody into place in terms of their concentrations, in terms of their pressures, when they reach equilibrium, this reaction. Again, because just as quick as it sort of drops off to the product side, they're going to come back the other direction just as quick. And what that'll do is just kind of keep everybody pretty much where they're at. And again, doesn't mean that we got equal amounts on both sides. It just means they're sort of locked in. The other thing about equilibrium sort of reactions, again, is it may appear that the reaction is sort of over, if you will, if you kind of look at the big picture. But if you were to look deep into the beaker, you would have a lot of activity of A and B's going to C and D's, and then you would have C and D's heading back the other way. So there's a lot of activity that's continuing to happen in an equilibrium reaction, even though, again, it may appear to you that the reaction is actually over at that point. Now, there is a relationship for an equilibrium, and we could use, say, this equation here. And we basically take our concentration of our products divided by the concentration of our reactants. And we do, in the case of equilibrium, take the coefficients into account. So K would equal the concentration of our products to each of their sort of coefficients. And when we do it with concentration, as we talked about, that is what is sometimes referred to as the Kc value, C being for concentrations. Molarity is typically the concentration unit that we use with this. Also, we could, if we had gases involved, we could actually do the same sort of equilibrium with pressures. And this is what is known as the Kp. This would be the partial pressure of C to the C, and D to the D divided by the partial pressure of A to the A and B to the B. Again here, Kp for pressure. Typically speaking, if you're doing some type of equilibrium calculation involving pressures, probably atmospheres is the units that you want to use in there. So that's sort of the standard unit of pressure. There's a relationship that we talked about going between these two things. The Kp value will equal the Kc RT delta N. R is the gas constant. It's actually the one that's used in the ideal gas law. That number, again, not the one that's energy. That is temperature in Kelvin. This is the change in the number of moles. So that is the moles of the product minus the moles of the reactant. Whatever ones are gases is what you would do. Basically, all the gas on the product minus the gas on the reactant. This allows you to go from Kp to Kc. Again, if you're just given maybe information about pressures, you can calculate the Kp, and then you can use that to calculate the Kc and vice versa if you have that. Remember that more importantly as well, when we look at K, which is a capital K, not a lowercase k like in the rate constant, it is a constant value for a reaction. Really, the only thing that will affect the actual value of the equilibrium constant is temperature. So as we talked about, what we're talking about with that is a comparison of the equilibrium constant, say at 25 degrees versus 50 degrees, the values will be different. But if you do a bunch of reactions all at 25 degrees, like we talked about, and again, as we also talked about, starting with all reactants, products, a little bit of everybody, they will all come to rest at the same equilibrium constant value. It is no units associated with this guy, which is good. But it does tell us if we have a large value of K, when we reach equilibrium, we would mainly expect to have products there. Again, large number on top, small number on the bottom gives us a large value for K. And if we have a small value for K, we expect to have mainly reactants when you reach equilibrium. Again, small value, larger value on the bottom, smaller value up on top will give us a small value of K. There is definitely degrees of that, as we talked about. You could have a really, really large value of K. You could have a really, really small value of K, and anywhere in between. For all intents purposes, a large value is anything 1 and above, basically. So anything kind of above 1 is considered a large value. Any questions on any of that stuff we talked about last time there? Okay. So we also got into this, I think, last time as well. And just to reiterate, there are a couple of things that are not included in the equilibrium expression. And we see it in this reaction, which is a heterogeneous equilibrium. Heterogeneous meaning that things are in different phases. The two things pretty much that do not affect equilibrium constant are solids and pure liquids. So if you have any guy that has an S next to it or an L next to it, we do not include those in the expression. So here, because calcium carbonate is a solid, we would not include it. Because calcium oxide is also a solid, we would not include it. That means for this particular reaction, the Kc expression is really just a concentration of the CO2. Also, the Kp in this case would be our CO2 as well. That means there's really two things that get included. That's things that are aqueous, and that are things that are gases. So these guys get included in the equilibrium expression. And you think about it, those are pretty much things that are pretty much always moving and doing things, right? So gases are flying around. Aqueous things are typically solutions, which are typically ions, and that means they're floated around in the solution, right? Ready to sort of react and stuff like that. Any questions on that there? And again, that's the idea. If you really do have a solid, it's just really sitting there, not doing much. The only way it could really participate is if it dissolved, and at that point, it's no longer solid. It's going to be aqueous, which you would participate at that particular point. All right. So why don't we try this one here? The partial pressure of each gas is 0.265. What is the Kp and Kc for this reaction at 295 Kelvin? Take a look here. So obviously in this case, we're given some pressures. So Kp would seem like the good place to start. We'll write our Kp expression. So that's going to be the partial pressure of NH3 times the partial pressure of H2S. Once again here, that is a solid, which means we're not going to include it, right? So this would be our expression. So put it in our numbers here. We'll have 0.265 basically squared. And that's going to get us there. We'll call it 7.02 times 10 to the minus 2 would be our Kp value. Again, no units necessary here for this guy. At that point, we can now use our equation. The Kp equals our Kc RT delta N. So we do want to figure out our delta N. So on our product side, 1 gas molecule, 2 minus, obviously this is a solid, so that would be 0. So our delta N in this case is going to be 2. The temperature already is in Kelvin, so that's good to go. We don't have to do the conversion. So that means that we have something like 7.02 times 10 to the minus 2 equals our Kc, our gas constant, sort of R value. and our temperature, which is already in Kelvin there, and we have a 2. So cleaning up on the right-hand side there, and do a little squaring. That's going to give us 7.02 times 10 to the minus 2 equals our Kc. And we got something like 586.0127393. We're going to take that, obviously, and divide it to the other side. And that will get us a Kc of 1.20 times 10. We got there 1, 2, 3, minus 4. So once again, in this case, as we saw previously, in a lot of cases, the Kp and Kc will not be the same numerical value. It can happen actually, but in a lot of cases it's not. But it does tell you the same thing. We have both a Kp and a Kc that's a small value, and we would expect probably mainly reactants there at equilibrium. Any questions on that one there? All right, so let's talk a little bit about equilibrium constants and equations. And there is a need sometimes, as you may know, and as we talked about, that not all reactions, necessarily occur in a sort of one-step fashion. A lot of reactions, again, occur in multiple sort of individual reactions, sort of like what we were talking about when we were doing reaction mechanisms. And also kind of like, if you remember Hess's law, perhaps, what you did in Chem 50, we got to add up all these equations together to get a delta H that's going on. So the same thing could happen in an equilibrium reaction. You may need to manipulate sort of an equation, or you may need to add a couple of equations together that have K values. So what we want to see is sort of what happens to our K value when we do that. So if we were to add these two reactions together, we would end up with this overall reaction here if we just added these guys together. Again, when you add reactions, anything that's on opposite sides of the arrow can cancel or reduce down. And then at the end, everybody on the left-hand side of the arrow stays on the left, and everybody on the right-hand side basically stays on the right-hand side, and you bring it down. If we were to write the equilibrium constant for this overall reaction, we get E times F and divided by A times B. Now, if we look at the equilibrium constants for each of these steps, that's kind of like the first step there, and that's kind of like the second step. The way that we get to this one is we actually multiply the K values. If you multiply the K values, those guys cancel, and that leaves you E times F divided by A times B. So when you are adding a number of equations together, you essentially will multiply the K values together. So not added here. That's kind of different than what you do with Hess's law where you add the delta H's. Here you actually multiply the K values together. So other ways that we can also manipulate equations is maybe we do not need our reactants on the reactant side and our products on the product side. Maybe we need them switched. So maybe our products need to be on the left-hand side and our reactants need to be on the right-hand side. So another very common way that we manipulate equations is we can do the reverse of the equation. And if we do the reverse of the equation, so this is with N2O4 as a reactant, and obviously this is our N2O4 as a product, basically the reverse of it. What that does to actually the equilibrium constant is it's actually 1 over the equilibrium constant. So also different than Hess's law, you don't just change the sign or anything like that. It's actually 1 over it. And that's because originally your reactants was on the left and now they're on the right. So your reactants and your products switch places, which means when you do products over reactants, they switch places. So it's the inverse of the K value. So if you find yourself that you need to reverse a reaction, an equilibrium reaction, and you need the K value for the new reaction, you need to take 1 over the equilibrium constant value, and that will give you the correct value. Now, when you see an equilibrium constant value, it is specific for that temperature, as we talked about, and it's also specific for the way the reaction is written. So if we were to look at these two reactions, and I say I have an equilibrium constant of this guy, That is specific for the N2O4 being the reactant side, the other guy be on the product side. If I say I have a K value of 216 for this reaction, it would be specifically for how that is written. So however the reaction is written, it will have a specific K value that's associated with it as well. Now, what are other things that you might do to manipulate sort of equations, which are very common? So obviously, if we add them together, we're going to multiply the K values. If we reverse the reaction, we're going to take 1 over the K value. Now, sometimes some other very common things that you do is, let's just say we have this, and K equals 10, right? So what we want to do in this case, if we write the equilibrium expression, this would be C and D divided by A and B, basically, right? Now, let's just say that we did not need 1A, but we needed 2A's. So if I needed 2A's, I would need to multiply the entire equation by 2. Now, when I write the equilibrium expression for this, this is C squared D squared divided by A squared and B squared. The difference between the first equilibrium constant and the second equilibrium constant is what? I did what to it? I basically squared it. Yeah, so I multiplied by 2, so I squared the K value. That would mean in this case, K would be 10 squared, not multiplied by 2. So you would have 10 times 10, dare I say 100. I'll try it with no calculator, but we'll go with that. And again, you actually square it, not multiply, which is a common mistake that people make because of like Hess's law they have in their head. Now, let's just say that I actually were going backwards and I needed to divide everything by 2. And I want to get back to my original equation. That means basically I came through here and divided everybody by 2. That got me back to my original expression, this particular case. And now as I go from here to here, the difference between that is the square root of it, right? I basically took the square root of it. So I took a big old square root. I end up with this basically. I divided by 2. I took the K value and took it to the square root of it. So the K in this case would be the square root of 100, which would give me back to 10 in this particular example. Now, if I multiplied by 3, I would take the cubed root. I would take it and cube it, the K value. If I divided by 3, I would take the cubed root. Yeah, so if you need to multiply by a common number, you take the K to that number, whatever the common number is. If you need to divide by a common number, you take the root of it to that number, the K value. So again, if you divide it by 3 all the way across, you take the cubed root and so forth as you do it. So these are very common ways that you sometimes need to manipulate sort of these equilibrium reactions and their values to maybe figure out the equilibrium constant for an unknown reaction if you're just sort of given individual information. Any questions on the manipulation there? All right, so why don't you try one? We're looking for what the K value of the top one is based off of the 2 reactions there on the bottom. Okay, so let's take a look. So when you're doing this, really the best approach, keep it simple, just get everybody on the correct side of the arrows is a good idea. So clearly we see A and B on the right-hand side. Over here, A and B is on the left. So we do know we need to reverse that reaction. So that will give me 2C plus 2D goes to A plus B. When I reverse the reaction, that means my K is now going to be 1 over the K. Again, not negative, so we're going to take the inverse of it. Now I also need to get looks like E and F to the other side, and there's 2 E's. So in addition, I also need to reverse it and multiply it by 2. When I do that, reversing and multiplying by 2 gives me 2E plus 2F goes to 2C plus 2D in that case. I did a couple things there, so we want to keep track of it. We reversed it, which means we're taking 1 over our K value. We also times it by 2, which means we also need to square that, right? So we got to do both of those things because that's the way we manipulated it. Hopefully here we did it right. We got 2c on the left and right will cancel, 2d will cancel. That leaves us 2e plus 2f on the left and a plus b on the right, which is the equation we're looking for. So remember, the other thing here is when we add these together, we're actually going to multiply these two guys. Again, we're going to multiply them, not add them here. So that's going to take us 1 divided by 100, which is basically 0.1. We'll go K1, K2. So K would equal K1 times K2. And we're going to times that by 1 divided by 20 squared. And that's going to get us a K value here of 2.5 times 10. 1, 2, 3, 4, 5, minus 5, I think, there. Any questions on that? So kind of the same ideas maybe you've done with Hess's law. Just got to kind of keep track of what you did. And again, remember that when we get to this last part of adding these equations together, they get multiplied, not added, the K values. Questions on that there? Okay. Try one more here. What's the K value for this particular one here? Based on the top two equations. Okay, so let's take a look at this one here. Again, going to take the same approach and kind of get everybody on the right side, make sure we have the right amount. So I see N2 here, I see N2 in our final equation. I do need 2 N2s in our final equation. I have a half here. So to get me to 2, I think that's going to be a 4. I need to multiply that by. That will get me 2 N2 plus 12 divided by 2 is 6H2 and 4 NH3. In terms of my K, I didn't reverse it this time, but I did multiply by a common number of 4, which means I'm going to take it to the 4th power there in that particular case. Now for our second one equation there, we do have water on the left, which is where we need it. But again, I do need to end up with 6 waters, so that's going to require me to multiply this guy by 3. That will give me 6 waters, gonna give me 6 H2s and 3 O2s. Once again, in terms of my K, I didn't reverse it, so just multiplied by a common number. So we'll take this to that common number. In this case, we're going to cube it. Here we're going to add this together, make sure we got the right equation. And in this case, it looks like the H2s will cancel. And I think that is it. So we'll end up with N2 plus 6H2O goes to 3O2 plus R4NH3. Once again, we did get the equation we're looking for. We'll call this K1 and K2, for example. So the K value for this would once again not be adding, but be multiplying these numbers together. So again, we want to multiply those. So that's going to be a 411 to the 4th power. And we're going to multiply it by 0.345 to the 3rd, our cubed. And that will get us something like, we'll go 1.17 times 10 to the 9, I believe, in this case. Any questions on that there? So again, very commonly, you may be giving some individual sort of equations that have equilibrium constants. You may need to use those and have to manipulate them to perhaps figure out the equilibrium constant of an unknown reaction. Any questions on how to do any of that there? So as we saw there, just to summarize and finish up here for today, when we do write the equilibrium expression, remember that when we talk about concentrations, they should be in molarity. And if it's any type of gases, again, atmospheres is usually the one that you want. Even, again, if they sort of give it to you in some other units, you got to kind of convert it into atmospheres to use it in the equilibrium calculation. Again, solids and liquids are excluded from our equilibrium expression. That leaves us, again, aqueous and gases. no units on our equilibrium constant. When we do see an equilibrium constant, it is specific for the reaction exactly the way it's written and the temperature that it's at. And again, if we start adding equations together like we just did there, we're going to multiply our K values. And obviously, if we reverse an equation, we're going to take 1 over the K value. And what we just did there in those examples, if we multiply or divide, we multiply, we're going to take it to that power. And if we divide, we're going to take it to that root, basically the K value. Any questions on any of that there? All right, let's get laying up place there for today, I think.